Here we're going to implement a state machine that counts down from 5 and then sets an alarm. So our state machine is going to start at state 5, 1, 0, 1, and then count down start bit or start state, and then we count down to 4, 3, 2, 1, and then at state 0 we set an alarm. And when we transition down, we always count down when the input is either 0 or 1. The output is going to be 0 until we get to the first state, or the state 0. So on state input 0, or on input 0 or 1, we're going to output a 0. On input 0 or 1, output a 0. On input 0 or 1, output a 1. And then on state input 0, we're going to output a 1 again. So reset, count to 5 if I equals 1 and state count is 0. Else count down. This is our word problem to specify this state machine. And since here we are in state 0, 0, 0, if we take an input of 1 here, then we're going to output a 0, and we reset to state 1, 0, 1. This notation here is shorthand for saying that we have one edge, input 0, output 0, and a second edge, input 1, output 0. So this edge represents these two edges here. Let's remove these two edges so we have the shorthand notation for this state machine. We now can draw the state diagram. The first thing we should notice is that we have only 6 states. 6 is not a power of 2, or not an even power of 2. Log base 2 of 6, well, 2 is less than log base 2 of 6, which is less than 3. However, the ceiling operation of log base 2 of 6 is equal to 3. So the number of bits, n, is equal to 3. Let's draw our state machine truth table. We have an input I, state bit A, state bit B, state bit C. Then we have output O, next state bit A plus, next state bit B plus, next state bit C plus. Let's list all possible input combinations. There are 4 input variables, so we have 16 rows. 4, 5, 6, 7, 8. Let's separate our table out into sections of 4 rows so that it's easier to list it out and identify which bits go with which row. Two, three, 4. And let's do input variable A. 1, 1, 1. Zero, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and then alternating bits 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. Now, let's look at our state diagram. We have 2, 4, 6, 8, 10, 11, and 12 total edges. Remember, we're using two-hand or shorthand for many of these edges here, except for these last 2. These are not shorthand edges. We're not using one edge to represent 2. But 12 edges. How many rows do we have? We have 16 rows, but 12 edges. How do we handle this? The answer is we're going to use don't cares for our outputs. First of all, let's go through and handle the rows that we do care about. So, let's look at state 0, 0, 0. Input 0, we're going to have an output of 1, and the next state is 0, 0, 0. For state 0, 0, 0, input 0, or state 0, 0, 1, input 0, the output is going to be 1 again, and the next state is going to be 0, 0, 0 again. For state 2, our next state is going to be 0, 0, 1, and our output will be 0. And for state 3, our output will be 0, and our next state will be 2. For state 4, input 0, our output will be 0, and our next state will be 3. So our output is 0, our next state is 3, 0, 1, 1. State 5, We have an input of 0 here. So our next state is 4. Output is 0. Next state is 1, 0, 0. But what about state 6? What about state 7? We don't have these states. So these are don't cares. We don't care about the output. We don't care about what we see for the output of X, of the output bit. We don't care what the next state is for either of these states. Because by design, this state machine should never get to states 6 and 7, because the state machine doesn't list it in this state diagram. So that covers inputs 0. What about input 1? Well, on input 1 in state 0, 0, we go to state 5, and our output is 0. On state 1 and input 1, our output is 1. Our next state is 0, 0, 0. On input state 2, we take an input of 1, our output is 0, and our next state is 1. Input 1, our output is 0 again, and our next state is 2. 4 goes to state 3. Output is 0 still. 5 goes to 4. Output is 0. And then for these two, we don't care about the outputs again. And we don't care about the next state equations. We can now create k-maps for each of our variables. Output O. We have I, A, B, C. We're going to take it from this column, going straight down the line. Let's label our columns and rows. One, one, 0, 0. 0, 0, x, x, 0, 1, 0, 0, 0, 0, x, x. Output O is taken care of here for the time being. Let's optimize it and group it in just a moment. Let's look at A plus. I, A, B, C. We're now going to look at this column. 0, 0, 0, 0, 0, 1, x, x, 1, whoops, 1, 0, 0, 0, 0, 1, x, x. Let's look at the next value for b, which is b plus. I, A, B, C. So the reason we're not optimizing these k-maps individually is sometimes if we can get a group that is shared across both k-maps, it is possible to save even more gates. So we're looking to take advantage of this if at all possible. It's not guaranteed that we can though, but it never hurts to look. Now we are going to look at this column 0, 0, 0, 1, 1, 0, x, x, 0, 0, 0, 1, 1, 0, x, x. Then we look at C plus, the next value of C. I, A, B, and C. Oops. Let's just go through 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. And now we're not looking at this column anymore. We're now looking at column C. 0, 0, 1, 0, 1, 0, x, x. 1, 0, 1, 0, 1, 1, x, x. So, how do we solve this? Well, let's start with O. We have a group here and a group that wraps around. So O equals I prime, A prime, B prime, or A prime, B prime, C. What about A plus? The largest power of 2 group would be this square. And then we have a singleton. So let's keep this in mind. A plus equals A ANDed with C, or I, A prime, B prime, C prime. Let's box our Boolean equations so that we can keep track of them. What about B plus? I see a large group here because of the don't cares, and I see a nice large group here wrapping around because of the don't cares. We can increase the group of 2 to a size of 4 with the don't cares. Let's take advantage. So the first group, B and C, or A and C prime. Finally, our last bit, C plus. I see a group here, and there is a group here. Then we can cover a third group here and here as well. Pretty ugly. So 4 groups. So we have B, C prime, or I, A, or C prime. Well, actually, let's call this I, C prime, and then we'll OR it with A, C prime. And that gives us our 4 output, our 4 combinational logic output bits. Let's try drawing the circuit. How many state bits do we need? Well, we're going to need 3 flip-flops. Let's draw those. D clock, Q and Q prime, reset, and we're going to place the preset signal as well. Let's place a second flip-flop. We need a D input, clock, reset, preset, Q and Q prime. And then our third flip-flop. This will give us our 3-bit register. Let's wrap this around. So this gives us C, C prime. Let's get B prime and B. And then we bring back A prime and A. So we can label these A prime, B, B prime, C, C prime, and we can see that they wrap around to their outputs respectively. The register or the flip-flop outputs respectively. And then we need to consider our input variable, I. Do we ever use an inversion? Let's box our equations. Do we ever use an inverted I? I am seeing one inverted I for the output. So we should list I, input I, and its inversion. I prime. Let's bring out our clock signal. And let's consider, what is our start state? Is it 0? No, it is 1, 0, 1. So when we reset the system, we do not wish to start in state 0, 0, 0. We wish to start in state 1, 0, 1. How do we start in state 1, 0, 1? Well, we can connect our reset signal to preset, to reset, and to preset. And then connect the reset signal here, the preset signal here, and this reset signal here, I'm going to bring it across to logic 1. We will call this VDD. Recall that VDD is logic 1. And we can label the clock input and the reset signal input. I is labeled, our state variables are labeled, the inversions of these signals are all labeled. Let's see if we can implement them now. C+ is particularly complicated. Let's try implementing that. So we need B and C prime. So we will take B, C prime. So C prime, C, B prime, B, and C prime. We'll need another AND symbol for I, ANDed with A. I ANDed with C prime. Do apologize, it is a little messy. And then we need A ANDed with C prime. So we can OR these four signals together. And we are there. What about B+? Recall that notice that we have a C prime in B plus and an A C prime term in C plus. We can share this. Let's draw the BC term first. B ANDed with C. And then we can OR this together. With A C prime. And we have saved one logic gate. Let's connect B plus and C plus together. What about A plus? AC, I, A prime, B prime, C prime. Yes, that is the condition where we have the singleton. AC A C, and then we need a 4 input AND. We need I ANDed with A prime, B prime, and C prime. It's a little tight here. So we can OR these together. And connect this to our A plus input. And now our O, I prime, A prime, B prime, A prime, B prime, C. So we need 2 3 input gates. I prime, I prime, A prime, B prime, A prime, and B prime. And A prime, B prime, and C. And now we have put it all together into a final digital logic circuit. A little bit messy here. Oh, we missed one gate, the OR gate. We OR these together, and this gives us our output, O. We can now try simulating this as well. I encourage you to try plugging this into the simulator and testing it out to see what the countdown alarm state machine looks like when it's in motion. Let's build the circuit for the countdown from 5 alarm. We have copied over the truth table equations that we optimized with K-maps over to our simulator here. So now we don't have to go back and forth between the notes that were taken in the previous program. Let's just start implementing the state machine directly. We have A plus, B plus, and C plus. So we have 3 state bits, n equals 3. Let us go to the library simulation logic if you are using LogicWorks. Again, you can use your own simulator if you like. Go to simulation logic and we will select a D flip-flop. We need 3 of these for 3 bits. 1, 2, and 3. Now, when we think about our reset state, we wish to reset to the state 101. So we need to keep in mind that we're going to be tying the reset signal high for the first and third, or the first and third bit, A and C. B is going to be tied high on the set bit instead. So let's leave enough space for these D flip-flops so we can tie them to logic, tie a logic 1 if necessary. Let us bring our signals around. Whoops. We have C prime. We'll bring the equations over here. This is the signal C, the least significant bit. Then we can bring over the signal B. Or B prime and then B. Previous signal was B prime. And now we can bring over A prime. And once we bring over A prime, we can now bring over A. This gives us our three feedback signals and their inversions. Let's bring in our input, and we need an inversion, so we need I prime as well. So we need an inverter for I. This is for I prime. We'll copy and paste this to develop the signal in I prime. Simulation gates. Let's place an inverter, also called a NOT gate. Actually, maybe a better location for the NOT gate would be further down. And then we can tie our logic gates to all of these signals as needed. Let's label our signals now. We have I prime, A prime, B prime, C, and C prime. So we have prepared all the signals that are going to be input to the combinational logic blocks. That will be defined by these characteristic equations. Let us develop the output O. Output O. We have 2 3-input ANDs and a 2-input OR. And a 2-input OR. We can connect the AND gate outputs to the OR input. And then we have for our first gate I prime, A prime, B prime. I prime, A prime, B prime, and then we have A prime, B prime, C. It may be possible to optimize this circuit. I've just left these as two-level logic circuits, sum of products form. And then we can develop A plus, which is AC, or I, A prime, B prime, C prime. So we need a two-input AND here, and a four-input AND. We'll take an AND 4. We need to develop AC, or I, A prime, B prime, C prime, A, C, or I, A prime, B prime, and C prime. These connect to an OR gate, or 2. Like so. Then we can connect B plus, which is BC or W, and C plus, which is BC prime IA or IC prime. W should be the last gate we use. So first let's place BC. It's an AND 2. And then AC prime. That's also an AND 2. So we have B. That's connected correctly. And C. And then we need AC prime. A, C prime. We can connect these to an OR 2. Now we're leaving a little bit of space here for our final equation. AC, or W, comes from this signal, so we can label this signal W. Not Q, but W. And let's move the label just a little bit so it's a bit clearer. And we can implement the C plus equation. So we need 3 more two-input AND gates. 1, 2, and 3. We can move these down a bit. These feed 1, 2, 3, 4 to a 4-input OR gate. So let's grab an OR 4 here, and we can connect first W. Then we need BC prime, B ANDed with C prime. We need I ANDed with A. Then we need IC prime. Again, you can very likely optimize this further to reduce the number of gates. I've just left these as two-level sum of products form circuits, but feel free to optimize these further. And now we've completed the combinational logic. We can do a final connection here. So now we have all our combinational logic circuits connected to the flip-flops, and our feedback path is complete. The input logic gate inversions are developed as needed. We can now prepare the connections for the clock signals, the reset signals, and the set signal. Let's use a 3-wire bus. So one wire bus will be connected to clock, another will be connected to the state machine reset, and then a third one will be tied to logic 1 or VDD. So let us connect our clock. All 3 flip-flops connect to the clock signal. 1, 2, and 3 flip-flops. And then we need to connect our reset signal. We reset to state 5. We reset to state 5, 1, 0, 1. So we need to set active low on our reset or on our set signal for the high order bit. We reset to logic low for the middle bit and set to 1 for the low order bit. Let us make sure that the reset state is set appropriately. Finally, we tie our remaining pins to a logic 1. Let us connect logic 1. I just use a plus 5 volt connection. Also, we need to now connect our observation points and our control points. So in LogicWorks, we use binary switches and binary probes. We'll place a binary probe at the output, and we shall also place binary switches for the input and also for the clock and for the reset signal. So we have an alarm circuit now. A little bit difficult to see. So let's zoom out a little bit. Zoom, reduce. Thankfully, we can still see the output and the binary switches. Notice that we are reset. For observation purposes, it will be helpful to look at which state we are in. Let us place some binary probes to list the state. A, B, and C. Connect to A, connect to B, and connect to C. And we see we are now in state 101. Every time we have a 0 or a 1, we count down. It should count down until we hit state 0, and then when we hit state 0, we should see an alarm. And then when we reset the alarm, we'll see a 0 on the output again. So let's clock. Go down from 5 to 4, 3, watching this, state 2, state 1, state 0, and we've seen the alarm. So we clock to state 0, and we are cycling. Let us reset the alarm now. Reset. We are now in state 5. The alarm is off. When the input is 1, it won't reset the alarm until we get to state 0 again. So let's continue. 5. Watch it count down. 4. Whoops. We now see an error here. What is interesting is we are setting to state, we're setting the reset signal, but this should only activate from state 0. For some reason, we are staying in state 5. Is this proper behavior? Let us look at the state machine. On input 1, it should go to state 4. Input 1 from state 5 should go to state 4. Let us look at what is happening. Well, 1, 0, 1 is state 1. 1, 0, 1 is state 5. We should see 1, 0, 0. The difference between 1, 0, 1 and 1, 0, 0 is this single bit here, C+. Very likely we have an issue. Perhaps on this circuit with the OR gate and these 4 AND gates. Did we implement this function correctly? Let us take a look. If the truth table, here we have input 1, and we are in state 1, 0, 1. This is the transition we are interested in. State 1, 0, 1, input 1. We should go to 1, 0, 0. Let's take a look at the truth table. 0, 1, 0, 1. We see an error that has appeared right here. This should be a 0. So let us change this now. That should be a 0. We actually have an error in our C+ table. And what we developed here is actually incorrect. Let's try changing this now for C++, or let's try changing this now for signal C+. The only difference is the last 4. So the bit that we're interested in changing is this 0 right here, which means that the group IA, we can delete that because this one is already covered. So let's cross out IA. We can go to our simulator. Let us modify our equation, remove IA, and then IA is this AND gate here. I ANDed with A right here. Let's take this gate and just delete it. We can connect this input here to a logic 1. Let's connect this to a logic 1, ORing with, connect it with a logic 0. This is an OR gate. If we connect with a logic 0, then we are ORing with 0, which means ORing with 0 is a null operation. We can simplify. I will remove some extraneous wire here. And let's try clocking now to see if we can go from state 101 to 100. 101, check the output at 0. Clock, it goes from 101 to 100. Okay. Next we should go to state 011. 011. This is correct. Next we go to state 010. We maintain our output 0 because the alarm is not going off. 010. Let us clock again. 001. And now we should see an alarm. Now that we are in our final state, 000, our alarm is going off. Our alarm is going off. Whether we reset or not, we see the alarm go off. And if we set it to 0, we're going to stay in state 000 until we decide to reset the alarm again, and we are back in state 101. What is interesting about this presentation here is we went through the development of a state machine that includes a number of states that is not a power of 2. We have only 1, 2, 3, 4, 5, 6 states. Notice that we list the extra states which are represented by the D flip-flops. There's always a power of 2 states, but the states that we don't use, we can list them as don't cares here and here in the edge graph or in the truth table because they're not shown in the state diagram, right? So this can be useful in simplifying our digital logic circuitry significantly. If we listed zeros or ones for these x's, the state machine would still be correct, but we would have more logic gates for O, A+, B+, and C+. Another issue we discovered was that even though we went through our circuit and we were able to develop a diagram, it's still possible to have errors. If you have the opportunity, take the time to check by hand to see if it works, or even better, simulate the circuit to verify that it's correct. So hopefully this demonstration of how to simulate and develop a state machine has been very helpful. And also some of the techniques used for debugging may be helpful in your digital design.